What's up, people? How's it going? Welcome to my channel, CP with Sundar. So, lately this channel has been a bit inactive, so I thought why not do a series of problem solving, which is both engaging and at the same time helpful. So, I came with an idea to solve problems which are mostly based upon binary search and binary search on answer. As seen from outside, binary search can be a very simple topic, but it involves a lot of intrications, which makes it an important and hot topic for CP. And binary search can also be used in many different ways, and one such thing is the binary search and answer. So basically, in this video, we'll be looking at binary search and different implementations of binary search, which will lead us to binary search and answer in subsequent videos. So without any further ado, let's get started. Now, what is binary search? So as everyone knows, binary search is a searching technique or searching algorithm which runs in logarithmic time. The basic functionality on which this binary search works, or the monotonic function, and the decrement of search space. So whenever we apply a binary search function, these two functionalities should be satisfied. So that is, the function on which we are applying the binary search should be a monotonic function, and the search space of the subsequent moves should be decreasing. And what is monotonic function? So monotonic functions are that type of functions where the characteristic is not changing at all. So it should be either fully decreasing or fully decreasing in its entire domain. Let's say y is equals to x. So this is always a monotonic function because it will always be increasing. These two functionalities are implicated already when we apply a binary search. So the basic binary search goes like this. I assume everyone would be familiar with the basic binary search. So in the standard binary search algorithm, we'll be having two variables, lower and higher. So let's say we keep a variable called L, and it is initialized to 0, and the higher will be initialized to the last element, last index of the element. So 0, 1, 2, 3, 4. 4 in this place. And usually we'll be finding out the mid value equals to L plus H by 2. And then we'll be checking whether the current element. So if array of mid is equals to the target element. So if it is equals to, then we'll be breaking the loop over there. So we'll be returning the index of it, which is nothing but mid. Otherwise, if the current element is greater than the target element, then we have to shift the end pointer to mid minus 1. So h will be becoming mid minus 1. Otherwise, L will be equals to mid plus 1. And we'll be running this loop till L is less than or equal to h. This is standard binary search algorithm that we are familiar with. Now let's say I give you a different scenario. Now I want to find the minimum element which is present in the array, which is just greater than or equal to the target element. So I want the index of the element or just the element. So find index of element which is just greater than or equal to the given target. So let's take this example. So here the array elements are 1, 3, 6, 7 and 9, and target element is 4. And now as we can see, 4 is not present in the array. So binary search, this functionality will not be directly working. And if the element is not present, so we should be returning minus 1 in this case. So that's how binary search works. So if we apply this binary search algorithm, then we'll be getting minus 1 because the element 4 is not present in the array. So I want to find such an index of the element, and it should be minimum index, which is having a value that is just greater than target. And in this place, it will be 6 because 6 is the element which is just greater than the given target, this 4. And if you also see, 7 can be an answer because 7 is also greater than 4, but it is not the smallest element that is greater than 4. Now how can we do this problem using binary search? So this is where we'll be actually looking at the functionality of monotonic functions. So can 1 be my answer or not? So when can some element be an answer? So the element can be an answer when it is greater than or equal to target. So 1 is not greater than target, so I'll be marking it with false. So can 3 be my answer? No, because it is less than 4. Can 6 be my answer? Yes, it can be my answer because 6 is greater than or equal to 4. So true for this, and 7 can be my answer, and true for 9 too. Now I want to find the first value in this particular array which is true. Because if I find the first element which is true, then what does this true indicate? So this true indicates that the element is already greater than or equal to the target element. So I want to find the first element which is true in this case. Problem converts to this. So find the first element that is true in the below array. Now, after thinking a bit, we have found a pattern for this. That is, we have to find such an element which should be given true as the answer. So anyway, we will not be calculating this array as it is, as we have to compute the answer in log n time. So if we construct this array, then even that will be costing us a time of big O of n. So we will not be constructing this. But what I'm trying to say is, we should find such an element which is giving true as the answer, and that will be the index which we are looking for. So the element which we are looking for is present at this particular index because this is the first value which is giving true as the answer. And even this can be my answer. That is, 7 is a viable candidate for my answer, as 7 is not the smallest element which is satisfying this case. So we'll be shifting to the left hand side. Now how to solve this problem? Now let's say while doing the binary search, my mid value falls at this particular element, that is 3. Now I'll be checking whether this 3 can be a viable candidate or not. And viable candidate in the sense, the element should be greater than or equal to target. So as 3 is already less than 4, then this mid element is useless for me, right? So I'll be shifting my lower to mid plus 1. Because mid is a invalid case, so I will not be searching for mid anyway. So I should be shifting my lower to mid plus 1. So the first case is when element is less than target, what should I be doing? I should be updating lower equal to mid plus 1. Let's say I'm standing at 7 and 7 becomes the mid element. So it can be my answer because it is greater than the target element, which is 4. So 7 can be my answer. So I'll be shifting the end pointer to the index of 7. So I'll be shifting h to mid. And a point to note over here is, I'm not doing h equals to mid minus 1, but instead I'm doing h equals to mid. And this is because as 7 is a viable candidate, so we may never know whether there is an element which is less than 7 or not at this point of time. So 7 can be my answer, so I'm updating h equals to mid instead of h equals to mid minus 1. But here I know that mid can never be my answer because 3 is less than 4. So I can directly update L equals to mid plus 1 instead of L equals to mid. So whenever the element is greater than or equal to target, I'll be updating h with mid. When should I be breaking the loop? So I can break the loop when L is less than h. So this is the basic approach for this problem. So we'll be initializing L with 0 and the highest element, that is the n pointer, to n, that is the size of the array, and not n minus 1. So let's say I give you an array. Let's take the same example. And I give you the target element as 10. Now if you see, all the elements will be failing because 1 is less than 10, 3 is less than 10, 6 is less than 10, and so is 7, and so is 9. Now, there won't be any answer which will be true in this case. We'll be taking L less than h. I usually take L minus h whenever I do binary search, but I have also seen many implementations where people take L is equal to less than or h and so on. So it's just a matter of preference. But I usually stick with L less than h. So in this case, L and h can never be equal to each other. So if they are equal to each other, then it will be breaking. So I usually go with L equals to 0, h equals to size of the array, and not n minus 1. So the first thing is while less than h, and L is equals to 0 and h equals to n. And if the value is false, then the current value, that is L, should be updated with mid plus 1. And in the case of true, then h should be made to mid. So at last, whether the element is present in the array or it is out of bounds. So the final index, that is the element which is greater than or equal to the target element, will always be found at the place of L after doing all the computations. And if you go to this problem, you'll be noticing that it is the same problem. So given an array of n elements sorted in non-decreasing order, which is nothing but it can be increasing or equal but not decreasing, and k queries. So for each query, find the minimum index of an array element not less than the given one. Now we'll be writing the solution for this problem. Now let's get started with the implementation. So the first value is the number of elements in the given array, and the second is for the number of queries, that is k queries. So n comma k. And now we have to get the inputs for the array. So I'll not be declaring an array, but inside I will be going with vector, which is dynamically allocated and it is a part of STL. So n number of elements and of I. So now we have got the input for all the elements of the vector. Now I had to get k queries. So while k minus minus. Now inside I'll be getting the query part. So here, this is where I'll be running the modified binary search. Modified binary search. So it will be calculating the first element that is greater than or equal to the given target. I'll be declaring two pointers, a low pointer which has the value of 0 and a higher pointer which takes the value of n, that is the size of the array. And now while L is less than h, which is the breaking condition, I will always be calculating the mid value, or this L plus h by 2. And there is also an optimization over here. Instead of doing L plus h by 2, I can break the statement into L plus h minus L by 2, because it can lead to integer overflows. So that's why we are abiding with the second option instead of going with the first option. So mid will be equals to L plus h minus L by 2. And now, if the current value, that is V of mid, so if this value is greater than or equal to the target value, now what is the target value? So at first I had to declare and get the input for target value. Now if this is greater than target value, that means that this particular index is a viable candidate for being my answer. So h will be equals to mid. Now in the else part, I'll be making L equals to mid plus 1. And when I come outside this while loop, I just need to print L. And one more thing to note over here is they're using 1 base indexing, but here we are using 0 base indexing. So I had to print L plus 1 instead of just L. I think this is perfectly valid. So let's run this code over the sample inputs. So we are getting 1, 3, 4, 1 and 6, which is perfectly matching with the sample outputs. So let's try submit in this code. So it got accepted. So this is how we can modify the standard binary search algorithms and solve many varieties of problems. And this can be done in a very simple manner. And there is already a inbuilt function in C++ STL. So it goes with the name of lower bound. Let's say I declare a variable called position, and I call this lower bound function, and I had to give the starting iterators and the ending iterators. So b.begin and b.end. And the target will be target, and this will be giving as the iterator to such an element which is greater than or equal to the target element. So to get the position of it, I have to subtract the starting pointer or the starting iterator. So v.begin. Now position will be having the index which is greater than or equals to the target element. So all we had to do is position, as we are using one based indexing, I mean zero based indexing. So we had to add 1 to this position. So let me run this code over the sample inputs. So here I'm getting 1, 3, 4, 1, and 6, and it's matching. So let me just try to submit this code. And even this got accepted. This is all for this video, and in the subsequent videos we'll be learning how to do binary search on answer, and we'll also be solving many good problems on binary search and answer. And until then, keep coding. Goodbye.